Hey, welcome back. This is now 9.5 on alternating series. Well, in this section, we'll also begin looking at doing approximations. So if you can prove it's convergent, you can kind of approximating it by using a certain number of terms, depending on how much error you're willing to tolerate. Okay, so anyways, let's take a look at the alternating series. First, we begin with kind of a definition or the form of an alternating series. And so let's take a look. So section 1, forms. We'll be given some a sub n, which is greater than 0, and then for the forms there'll be an additional factor of this negative 1 to the n or negative 1 to the n plus 1. Okay, so we kind of will think of the terms of the series as being separated into this negative 1 to the n portion times this a sub n, whereas previously we would think of the entire thing as a sub n, right? So it's a little bit kind of awkward. But anyways, the first form, if you're starting at n equals 1, the first term will be negative and then positive and then negative. Okay, so hence the name alternating. Okay, the second guy then, the first term, of course, is positive if you start at n equals 1 to infinity, and then negative, and then positive. Okay, and those are the forms. So the alternating series test will be another one of these kind of tests where you're establishing whether it converges or diverges, and you'll have some criteria to follow. So let's kind of show you what we have to do. So the alternating series test. And the test is done on the a sub n portion of the series. Okay, so again, we presume that the a sub n portion is greater than 0. Then the alternating series of either form will converge if the following criteria hold. Firstly, the limit of this a sub n formula has to go to 0 as n goes to infinity. And then secondly, you have to show that the terms of the series are basically decreasing. Okay, so in other words, a sub n plus 1 is less than or equal to a sub n. I think in monotonistic terms we said that that was non-increasing. Okay, so usually to prove the second statement, you're going to have to use your monotonicity test. So you're going to have to show, show a sub n plus 1 minus a sub n is less than 0 for all n, or show, and the second case is usually what I do, show that a sub n plus 1 all over a sub n is less than or equal to 1. So in both cases less than or equal to, but usually you can show it's less than and it'll be strictly decreasing. Okay. The proof of it is kind of a bit a lot to stomach. In order to do the proof, you first need to be able to kind of acknowledge, so sort of a helper fact, or sometimes they call that a lemma in math circles. Basically, if the limit of the odd terms of a sequence is equal to the limit of the even terms of a sequence, then you could say the limit of the terms of the sequence will equal whatever those two values are. So if the even and odd sequences of partial sums have limits and they're the same thing, that implies the overall sequence goes somewhere. So before, I think in like chapter 9.1, I established the idea that if the limit of the odd terms and the limit of the even terms are not equal, then the limit does not exist. And that's just basically the contrapositive of this statement. Okay, so if you negated this portion and said that suppose the limit of s sub n does not exist, you could conclude that the limit of the even and limit of the odds are not going to be the same. Okay. Anyways, let's dive right in here and kind of take a look at the alternating series test. Regardless of what other issues we have, we kind of, hopefully you can kind of stomach this. You could go back and prove it using the strict definition of a limit. I'll spare you the details and not do that, but anyways, let's dive into the proof, right? So we're going to consider the one particular form. You could do the other form. They both have the same kind of proof, but we'll use the form where the first term is positive. Okay, so for this series, we can write it out as s sub 2n. This the even term of the sequence of partial sums will have the form a sub 1 minus a sub 2, a sub 1 minus a sub 2, and then plus a sub 3 minus a sub 4 plus dot 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 plus a sub 2n minus 1 minus a sub 2n. So for this series that I just wrote, for this series, the this thing s sub 2n has all non-negative terms. Okay, so s sub 2, s sub 4, s sub 6, s sub 8, all the terms in those are non-negative. Okay, thus we have that the sequence of partial sums of the even terms of this sequence of partial sums, this thing is non-decreasing. And it's because if you go from s sub 2 to s sub 4, they're all positive terms. If each one of these things is a positive term, in order to go from s sub 2 to s sub 4, you're just adding something in that's positive. Okay, so it's always going to be increasing, in other words, non-decreasing. Okay, then also note another way you can rewrite it. S sub 2n can be rewritten as a sub 1 minus a sub 2 minus a sub 3 minus a sub 4 minus a sub 5 minus dot 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 minus a sub 2n minus 2 minus a sub 2n minus 1 minus a sub 2n. What does this say? This means that s sub 2n is bounded above by a sub 1. Okay, basically any version of s sub 2n is just going to be a sub 1 minus a bunch of stuff, right? So what you're getting then is an upper bound for this sequence of partial sums, the even terms of the sequence of partial sums. Therefore, the thing is non-decreasing and bounded above. Therefore, the thing is convergent by the monotonic bounded convergence theorem that we had in 9.1. So hence, this sequence of partial sums s sub 2n is convergent. Thus we can say its limit equals some number L. Okay, so thus the limit of s sub 2n equals some number L. Okay. Next, then, note we can write s sub 2n minus 1 as s sub 2n, and then so how would that work? That s sub 2n minus 1 would be like right here, right? Everything up to this point right here. So s sub 2n s sub 2n minus a sub s sub 2n would be sort of the same thing, but you would be adding in to get rid of this last term here. right? This a sub 2n. That's the only difference between s sub 2n minus 1 and s sub 2n. So if you add in a sub 2n, s sub 2n minus 1 will equal s sub 2n plus a sub 2n, because you're just adding this in, 2n, and then these guys would cancel, and you would just have s sub 2n minus that last term, basically, right? So then we could rewrite that by just subtracting a sub 2n from both sides. So I have s sub 2n minus 1 minus a sub 2n equals s sub 2n. And then you could take the limit of that thing on the left there. So note the limit of s sub 2n equals, of course, something. We said L above. And then that should just equal the limit of s sub 2n minus 1 minus a sub 2n, right? So, you know, we have at that point that something that we need. In particular, s sub 2n equals L equals basically the limit of s sub 2n minus 1. And it doesn't seem like we have it, but we do. We have that s sub 2n, the limit of s sub 2n is equal to the limit of s sub 2n minus 1, because the limit of all of the terms go to 0, right? If you look back at that form, that criteria, it's this first criteria that has to hold for this to pay off. Okay, so I mean, in the proof you're using both of these criteria. So if those two don't hold, then the proof won't work, and therefore you're out of luck. So here, the limit of this portion is just going to shoot off to 0, and you have that the limit of s sub 2n is equal to this number L, which is equal to the limit of s sub 2n minus 1. And then from our lemma, that basically implies that the limit of s sub n is equal to something. In other words, the limit of the sequence of partial sums is convergent, and therefore the series is convergent. Okay, so hence the sequence s sub n must converge. Which means the series, whichever one we are dealing with, this is n plus 1 times a sub n, is convergent. Okay, so again, knowing how the proof works kind of tells you why these particular criteria are important. Just the limit of a sub n alone equaling 0 would not be enough to convict this series as a convergent series. I mean, the nth term test for divergence would, that this does not fulfill that criteria. You couldn't say it's convergent just because the limit is equal to 0. It's combined with this other fact that it'll work out, right? The decreasing terms allows us to say that the thing is non-decreasing, and that first part we'll be able to establish that the even terms of the sequence partial sum are convergent, and then we could play a little bit of algebra and then do a limit here, plus the idea that the terms go to 0 gives us that the overall sequence converges, assuming that you accept the lemma that if the even and odd terms converge, that implies the overall sequence of partial sums converges. Okay, so there's that. And in practice, then it's a bit easier. Let's see what they have that are going to work with. So example 1, we have the given series -1 to the n plus 1 times 1 over n from n equals 1 to infinity. So again, you're doing the test on a sub n. You kind of don't even acknowledge this -1 part unless you were doing an approximation, which we'll talk about here in a second. So this part you kind of just throw in the trash, and this other part, I don't know why I rewrote it. The other part is the a sub n. That's what you're doing the test on. So first you take the limit of a sub n, and that equals 0, so that part works. And then you got to show that the terms are decreasing. Okay, so the way the book does it is it kind of just make a relation and say it works just by inspection. I would really want you to do either a difference like a sub n plus 1 minus a sub n, or the ratio a sub n plus 1 over a sub n, and show that that's less than 1, less than or equal to 1. So let's do the sort of the second version, the ratio version. Sometimes if you need to, you can do the calculus, like just look at f of x equals 1 over x and then take its derivative and show it's decreasing on that interval. But anyways, a sub n plus 1 is 1 over n plus 1. A sub n is 1 over n. Taking reciprocals and multiplying, this is n over n plus 1. This definitely is then less than or equal to 1. It's less than 1 for n greater than 1. Greater than or equal to 1, it's less than 1. So that implies it's decreasing, and therefore these two holding imply that the series is convergent. So hence the series converges. Okay, let's look at example 2. So example 2, the series n equals 1 to infinity of n all over negative 2 to the n minus 1. Okay, so the a sub n portion is it's not clear where it is, but you can rewrite this expression as n all over negative 1 to the n minus 1 times 2 to the n minus 1. Right? It's because of the product to a power rule. So if you have negative 2 to the n minus 1, that's the same as negative 1 times 2 to the n minus 1. And then you can kind of distribute the n minus 1 exponent to the two portions, and you get what I have in the denominator in the second step there I wrote. So then you could rewrite it as a sum of factoring the negative 1 kind of in front. Rewriting it like this is not going to affect it. You'll have n all over 2 to the n minus 1, and then this is your a sub n portion that you're doing your test on. Okay, so first do the limit of n all over 2 to the n minus 1. This is infinity over infinity, so you could do L'Hopital's. So the derivative of n is 1. The derivative of 2 to the n minus 1 is 2 to the n minus 1 ln of 2. And of course that will just equal 0 as n goes to infinity. Secondly, then you could do, again, I would do a ratio test. So a sub n plus 1, wherever you see an n, you're putting n plus 1. So n plus 1 all over 2 to the n plus 1 minus 1 is just n. And then all over n all over 2 to the n minus 1, right? So you could rewrite that doing reciprocals. You have n plus 1 over 2 to the n times 2 to the n minus 1 all over n. This is the same thing then as you can move the 2 to the n minus 1 to the denominator and subtract. So you'd have 2 to the n minus n minus 1. So 1 all over that times n plus 1 all over n. And then that would equal 1 all over 2 to the n minus n plus 1 is just 1/2 times n plus 1 all over 2. All over n. And then you have to compare that to 1. Eventually, yeah, that's going to be less than 1 eventually, right? At first it won't work, because when n is 1, it'll just be 2 all over 2. But then afterwards, it'll definitely be the case that n will be greater than n plus 1. In particular, 2n will be greater than n plus 1. So, yeah. Okay. I mean, you could prove that. The book likes to kind of separate them, so put the n over n plus 1 on the other side. Please don't do what the book does. Just do it my way. I mean, if you want to prove it from first principles, you would have to kind of start with what your n values are, right? So this is true for n greater than or even equal to 1, because we have the inequality is less than or equal to 1. So you could say n is greater than or equal to 1. Add n to both sides. So you'd have n plus n greater than or equal to n plus 1. So you'd have 2n greater than or equal to n plus 1. And then you can divide both sides by 2n because n is greater than 0. It's actually greater than or equal to 1. And you get n plus 1 all over 2n. And that's the inequality right there. Okay. So if you're still a little unsure, you can go back to sort of a direct proof would be what this thing on the margin was called. But you don't need to go that far. As long as you can establish, you kind of look at it and by intuition kind of say, okay, the denominator is going to be bigger than the numerator, therefore it's going to be less than or equal to 1. That's fine. But I need to see that inequality starting from here and then going to the inequality being less than or equal to 1. Okay. Let's see what else they have. So sometimes the alternating series test is not going to apply, and mainly that happens when the first criteria does not hold. So an example I stole from the book a long time ago: -1 to the n plus 1 times n all over 3n plus 2 from n equals 1 to infinity. The a sub n portion is right here. Okay, if you don't mind, I'm not going to rewrite it like that, so I'm just going to do my diagnosis on that part. So first I need to make sure the limit goes to 0, and of course it doesn't, right? If you do the limit of this thing, n over 3 to the n is 1 over 3, so this limit is just going to be 1/3, which does not equal 0. Okay. You may think it automatically implies that it's divergent. Not quite. The truth is you would need to go back to the nth term test for divergence. So noting the nth term test, you would really be looking at the limit of -1 to the n plus 1 times n over 3n plus 2. And of course, that limit would not exist. This limit does not exist because the odd terms are going to 1/3 and the even terms are going to -1/3. So the limit of the odds basically does not equal the limit of the evens. And that's why the thing is divergent. It's the nth term test. But for you guys on the test, I'll let you assume this fact. You would have to kind of prove it in general, to be honest, but I'll let you assume it. If that first criteria fails, you can presume that the series is divergent. Okay. From here, they're going to start talking about the alternating series remainder theorem. They don't really give a proof for it. I'll try to give you some intuition. So the alternating series estimation theorem. And basically, if you know the series is convergent, you can approximate the thing using Theorem 9.15. So if the series converges, basically the difference between the actual sum and the nth partial sum, which basically gives you a kind of remainder, it will be less than or equal to the next term in line. Okay, so to give you some kind of intuition, this won't be exactly a proof, this is kind of just a sketch of the proof. You can play with the terms of the series. So let's presume that we're dealing with the one where the first term is positive. So consider the series from n equals 1 to infinity of -1 to the n plus 1 times a sub n, and kind of look at the terms of the sequence of partial sums, right? So s sub 1 would be a sub 1, s sub 2 would be a sub 1 minus a sub 2, and not only so this thing is convergent, right? So basically the terms are decreasing. S sub 3 is a sub 1 minus a sub 2 plus a sub 3. Consider the picture, okay? So the intuition, we kind of have a picture. So you start at some value a sub 1 right here, and then you're subtracting away some value a sub 2, which is less than a sub 1 because the terms are decreasing. Okay, and then you're going to add in the next term in line. So adding in a sub 3 will kind of bring you over here. If you, I mean, on the bottom here, these should be s sub 1, s sub 2, s sub 3. And then the move is the a sub 1, a sub 2, a sub 3. So this first point here would be s sub 1. And then you're subtracting a sub 2. And that would bring you over to here, where is s sub 2. And then you're adding in a sub 3. So that would bring you to s sub 3. And then you repeat. So you're subtracting away then a sub 4. And that would bring you to s sub 4. And you're basically building a sequence where the even terms are increasing and bounded above, and the decreasing terms are decreasing and bounded below. And if you kind of continue this process over and over, you're going to eventually get, well, you won't exactly get there, but you'll get to this number s. And for any kind of lead into that point, what would happen? You would go s sub 2n or a sub 2n, yeah, and then you would be left here with s sub 2n, and then you would add in some other value, a sub 2n plus 1, and you would have your partial sum s sub 2n plus 1. So what's the point, Dave? What are you getting at? It's this distance here, right? If you look at that distance, in particular, just the distance between s minus s sub 2n, or the distance between s and s sub 2n plus 1, both of those distances will be less than this move here, which is given by minus a sub 2n, right? So for s minus s sub 2n, that distance, which is, let me put it in blue, this kind of distance right here, that distance, that is definitely less than a sub 2n, right? And not only that, it's less than a sub 2n plus 1, because that next term in line is going to take you from here over to here. Okay, and likewise, the distance between s and s sub 2n plus 1 is going to be less than or equal to the next kind of traveling distance, a sub 2n plus 2, right? So ultimately then you can make this statement that the difference between s and the nth partial sum is less than the next term in line, because the things will kind of be marked off by the a sub n plus 1. Okay, so I'm sorry if that doesn't make too much sense, but that's the idea of what's going on here. Right. Okay, so yeah, long story short, it's not all that hard to implement. There's two kinds of problems. Basically, you're trying to figure out how good is your approximation if you use a certain number of terms. Secondly, you want to know how many terms should you use if you want to get a certain approximation. So let's see if we can find one of each of those problems in the homework. Right. Let's see if I put any in here. Oh, so here's, maybe these are so number 10 is one of these. Did I only put one in there? No, there's another one. So number 8 is the kind where you're doing a certain number of terms and kind of figuring out how good the approximation is. Okay. So let's make number 8 also the video quiz. This will be the first video quiz in video quiz set number 7. Okay, so it's number 8 from WebAssign. And let's take a look. So we're trying to approximate the sum of the series using the first 6 terms. -1 to the n plus 1 times n all over 2 to the n from n equals 1 to infinity. So we know s then minus s sub, we want the first 6 terms, so s sub 6. The difference there will be less than or equal to the next term in line a sub 7. Okay, so the a sub n formula is this from this portion. So a sub n we know is n all over 2 to the n. So a to the 7th is going to be 7 all over 2 to the 7th, right? Zipping into my calculator, 7 divided by 2 to the 7th. 7 divided by 2 to the 7th is about 5/10, right? 0.0, let's see how many terms they want. 4 decimals. So 0.054, of course this is around 1, 2, 3, 5, 4, 7. Okay. So the difference between s and s sub 6 is 0.0547. I don't know what s is, but I can figure out what s sub 6 is. S sub 6 is going to be plugging in 1. I'll get -1 squared times 1 over 2 to the n. Then minus 2 all over 2 squared. Then plus 3 all over 2 cubed minus 4 all over 2 to the 4th. Plus 5 all over 2 to the 5th minus 6 all over 2 to the 6th, right? And then I can get an approximation for that. Let me just go to Wolfram to bother with that. There's Wolfram. And figure that out. 1/2 minus 2 all over 4 plus 3 all over 8 minus 4 all over 16 plus 5 all over 32 minus 6 all over 64. So I'm getting 3/16. And then you can sort of wedge s minus s sub 6 in between the positive and negative of a sub 7. So you'd have s minus 3/16 less than or equal to 0.0, or if you want to keep it real, you can put in the 7 over 2 to the 7ths and then get your approximation at the end. That might be safer. 7 all over 2 to the 7 is 128. And then greater than or equal to -7 all over 128. Add 3/16 to all 3 sides, and then you'll know kind of where s is, right? So let's try that. We have -7 over 128 plus 3/16, which is 17 over 128. And then let's get the decimal form for that. So we want a 4 decimal approximation. Of course, it won't give me 4 decimals, but yeah, it did. 0.1328 less than or equal to s less than or equal to positive 7 128 plus 3/16, which will be 31 over 128. In other words, 0.2422. Okay. So we know our answer is in between those two numbers. So let's put that in. 0.1328 and 0.2422. And I hope that's right. If not, I'll just go back and check it. Yay! Okay, so that's one type of problem. The other type of problem is when you're trying to figure out how many terms you need for a particular given error. Okay, so number 10 would be that flavor. So we have the alternating series n equals 1 to infinity of -1 to the n plus 1 over n cubed. And again, you're working with this formula: s minus s sub n needs to be less than or equal to a sub n plus 1. So you could kind of fill that in with what you need. You want a sub n plus 1, which is kind of the error, to be, and the problem tells you want the error less than 0.001. So you want a sub n plus 1 to be less than 0.001. Okay, so what the heck is a sub n plus 1? Well, a sub n is going to be 1 over n cubed. Again, you don't include the negative 1 portion, right? So I'll have 1 all over n plus 1 cubed less than 0.001, and then you could literally solve that inequality. You could also do trial and error, so start with n equals 1, and then n equals 2, and then n equals 3. But you could solve it just by going 1 has to be less than 0.001 times n plus 1 cubed. Flip-flop the sides, divide by 0.001. n plus 1 cubed is greater than 1 over 1,000, which will be 1,000. And then you can take the cube root on both sides. The cube root of 1,000. Is that just 10? Believe it or not. 1,000 raised to the 1/3 power. No. I wish it would. Yeah, it is 10. So you have n plus 1 greater than 10, and so n has to be greater than 9. In other words, use the theorem to figure out the smallest number of terms required to approximate the sum. So the smallest number of terms you get away with would be 10. Okay? It has to be greater than 9, so the smallest would be 10. And then you hope that's the answer. Drum roll. And yeah. Okay, great. Don't let these problems trick you. On the test, it's just asking for limits. All they're doing in these these problems where they're just trying to get you to determine if it's convergent or divergent, all they're doing is having you do the first step of the alternating series test. On my test, you do not do that. Okay, on my test, you have to do both steps. You have to show the limit goes to 0, and you have to do a ratio test for monotonicity or do a difference, right? So I did all ratio tests in order to prove that the thing was decreasing. So step 2, you have to show step 2. So some students last year weren't doing that, and they were probably disappointed at their grade. But no, you have to do what I say. And the time before WebAssign, it was people did it my way. Okay, that's the way we still want you to do it. The book just can't. The software is unable to kind of grade you in that capacity. So, okay. Anyways, after you get through these problems where you're approximating and you kind of acknowledge, okay, yeah, Dave was right, Mr. Stroop was right. All you have to do is get the first couple terms. I mean, we don't know exactly what the sum is, but if you just look at the first couple terms, you can approximate the sum, and you can even figure out how good your approximation is. So yeah, we don't need to know exactly what the series adds up to. We just need to know if it's convergent or not. And you should, technically, for number 8 and 10, you should be proving it's convergent first. Okay, but anyways, moving on. Our next topic is this. You can see it in the number 12. You want to figure out if something is conditionally convergent, absolutely convergent, or just divergent. So what the heck is all that stuff about? So let's take a look. I do a flow chart idea. So first you have to start with the series of the absolute value of the terms of the series. So you look at the series created by taking the absolute value of a sub n and ask yourself whether it converges. So let me kind of smush, does this series converge? That's where you start. Okay. There'll be two possibilities. Either it doesn't converge or it does. So no or yes, right? If it doesn't converge, or if it, sorry, it's the other way around. Let me put it the other way around just so I'm consistent with my notes. Sorry. So if it does converge, you're done. Okay. It's in that case, the series A sub n is considered to be absolutely convergent. So this series is absolutely convergent and therefore convergent. Absolute convergence is like awesome convergence. It has some other implications. Like one implication is no matter how you kind of mess around with the series, it will still converge, so you can change order of terms. I believe that was the deal. If it's not absolutely convergent, then you need to kind of go back to the original series and test that. So you ask yourself, does the original series converge? Again, there's two possibilities, either yes it does or no it doesn't. If it does, then that series is called conditionally convergent. So the series A sub n is conditionally convergent. If it doesn't converge, then you can automatically say the series is divergent. Okay, so let's take a look at this in action. Let me see what kind of problems we're looking at. Give me that one. And they got some extra problems where you're kind of okay, let's kind of go through them. Let's look at number, because I'm not sure whether they'll converge or not. Let's look at number 14. We got the series -1 to the n plus 1 times n over 4n plus 3. Maybe I should just go with the book, so use their examples. Okay, so they kind of don't follow my algorithm in the book, but I really think you should. I usually don't put these kind of questions on the test, but let's take a look at example 6, part A. So we have the series of -1 to the n times n factorial all over 2 to the n from n equals 0 to infinity. I just feel like my flowchart's the best way to go, because otherwise you're going to be kind of spinning your wheels and guessing. Anyways, so first you want to consider, if you look at my flow chart, first consider the series of the absolute value. So if you take the absolute value of that thing, the absolute value will kind of annihilate the -1 to the n portion. Okay, that thing won't affect it anymore. And so you could just rewrite this as a series of n factorial all over 2 to the n. Okay. If you look at the limit of that thing, limit of n factorial all over 2 to the n, because of what we know about the limit of k to the n all over n factorial being 0, the reciprocal of that is going to be infinity. It'll kind of be like an L, because this one is kind of like L over infinity. So if you take the reciprocal of that, it's kind of like infinity over L, and then it's going to go to infinity. Okay, kind of. It's kind of a bad way to describe it, but just kind of some intuition. Okay, it's not proof or anything, but based off this behavior, you can conclude this. That's not equal to 0. Hence, by the divergence test, by the nth term test, it diverges. But you haven't really said the original series diverges, right? So in the flow chart, what's happened is you've gone down this arm. So what you need to do then is go back to the original series. Secondly, you go back to the original series and say whether or not that thing diverges. -1 to the n times n factorial over 2 to the n. This is an alternating series, and the first step is to look at the limit of n factorial over 2 to the n. We just said that equals infinity, And if you remember back here, I said that when that happens, when that first step fails, you can go ahead and conclude that the series will diverge. Okay, so hence this series diverges. Okay, so if you go back to your flow chart and look, we started here at 1, it was no, so we went here 2, and then thirdly, again, we got another no, right? So your ultimate conclusion is that the series diverges. Okay, so that's part A, and they just kind of jumped to the chase. I kind of want to make it so it's programmable, so a computer could do it without thinking. This takes what they do takes somebody who knows what they're doing. So they don't always suppose that. So anyways, part B, again, we're looking at a series, -1 to the n over square root of n. We're going to start at the top of the flow chart and look at the series of the absolute value of the terms of the series. Okay. So again, the absolute value will get rid of that -1 to the n thing. You'll just have 1 over the square root of n. This thing is what? Well, it's a p-series. Secondly, the p-value is 1/2, which is less than or equal to 1. Therefore, it's divergent. And remember, you got to show those 3 pointers. So in the flow chart, we have gone down the right side. Okay, so no. So secondly, then you consider the original series. So the series -1 to the n all over square root n. This is an alternating series, so we try the alternating series test. So the first step I'll just write as I. We take the limit of a sub n. A sub n is 1 over square root of n. Of course, this will equal 0. And then secondly, we create an inequality, right? So we'll go a sub n over a sub n plus 1 all over a sub n. So a sub n plus 1 is 1 over the square root of n plus 1. A sub n is just 1 over square root of n. Taking reciprocals, I'll have square root of n all over the square root of n plus 1. And I think that's clear that the denominator will always be greater than the numerator. So that will be less than 1. That implies it's decreasing, so therefore it's convergent. Okay, so going back to the flow chart, what has happened? So first we said no, the series with the absolute values doesn't converge. We got to the second step here, does the original series converge? And we learned yes, it does. So in this case, it's called conditionally convergent. Okay, so hence overall, the series converges conditionally. Okay. Then looking at some harder ones here, I guess example 7. Let's look at part A first. And we have the series n equals 1 to infinity of -1 to the n times n plus 1 all over 2 all over 3 to the n. Okay. This exponent, the n times n plus 1 all over 2, that will give you kind of negative, negative, positive, positive, negative, negative, positive, positive. So it won't alternate in the kind of the traditional way. Anyways, so number 1, first we look at the series with the absolute value. So number 1, taking the absolute value, we just have 1 over 3 to the n. And that's clearly a geometric. Okay, so first it's geometric. Secondly, the r value, the absolute value of r, is equal to 1/3, which is less than 1, so therefore it's convergent. Okay, so in the flow chart, we're there. We're done. You know, we did the test on the absolute value, and we got a yes, so therefore the series is absolutely convergent. Okay, so we could stop there. Part B, then we have the series -1 to the n all over ln of n plus 1. N equals 1 to infinity. So again, first you start with the absolute value of the terms. So absolute valuing it will get rid of the -1 to the n thing. You'll just have 1 over ln of n plus 1. That looks like a, I don't know, I would say an integral test at first. But because it's 1 over ln, I don't think so. I'd probably have to do a comparison test. Noting that, how the heck could I even do that? I need to find something below it that diverges. So I think, I don't know. Sorry. All right, so I'll do a direct comparison test. So note, direct comparison. May have to be a little creative here. Test. So the first step, we need to do a comparison of 1 all over ln of n plus 1. I think it's going to be convergent. Okay, so I need to bound it above by something that is also convergent. And so I need that type of inequality to hold. In other words, I need to decrease the denominator, find something that's less than ln of n plus 1. So I want this other expression to be, I need to decrease the denominator, therefore increase this side. Decrease the denominator, make it smaller. Well, you can go ln of, you can use a constant like ln of 3 or something, but that's not going to get you anywhere because that wouldn't converge. You just need something that converges. So ln of 2, yeah, you could just go ln of 1. Well, let me pause the video. Looking, it doesn't, it's not going to converge. You can pull this trick, make it go above something by increasing the denominator. So n plus 1 is definitely going to be less than 2 to the n. Okay, so I have to be real clever. It's probably something that I wouldn't expect it to do on a test, but you can bring the exponent out in front of the ln using a power rule. So you got ln of n times ln of 2. So what you're ending up with there, that series of 1 all over n ln 2, that's a harmonic, right? That's just a constant multiple of the harmonic. If you could rewrite it again if you don't see it. This is the same as a series of 1 all over ln 2 times 1 over n, right? So this is constant multiple of the harmonic. The harmonic is divergent. Hence they both diverge. Hence this thing diverges. Okay, so this first step doesn't work. So in the flow chart, we have to go to the right and analyze the original series, which kind of looks like a alternating series So here now in step 1, I just want to bracket that off because I use the same numbers for the comparison test. So consider an alternating series test now on the original series, which is -1 to the n all over ln of n plus 1. Was that right? Yeah. So first, kind of look at the limit of the a sub n portion. That would be 1 all over ln of n plus 1. Of course, that goes to infinity because ln goes to infinity. So that will be 0. I mean, it goes to 0, right? L over infinity is 0. Okay. Secondly, then, you could look at a ratio. Kind of do a ratio of the terms. So 1 all over a sub n plus 1 is ln of n plus 1 all over 1 all over ln of n. That'll equal ln of n all over ln of n plus 1. The natural log is an increasing function, so it's fundamentally true that the ln of n will be less than or equal to ln of n plus 1. In other words, you could divide both sides by ln of n plus 1. That's a positive quantity, and you get ln of n over ln of n plus 1 is less than or equal to 1. So this will be less than or equal to 1, therefore it is decreasing, therefore it's convergent right here by the alternating series test. So your ultimate conclusion then is conditional. Okay, so I just assumed it would be absolutely convergent because the example, because we had done one example that was, conditional, one that was divergent, and it said absolute. I guess I didn't read it. Absolute and conditional convergence, whatever. Sorry about that. So anyways, let me just look at that for a second, make sure it was right with that inequality. So with the inequality, I needed to find some terms of a series that come from a divergent series that was below. So I needed to, on this thing, basically increase the denominator. So I basically just noted that n plus 1 is less than or equal to 2 to the n eventually, right? N plus 1, if you think about it, is just a line with slope 1 where the intercept is at 1. And then 2 to the n is an exponential curve. So that's just going to go off to infinity like this eventually. So eventually, yeah, it has to hold just from looking at the graphs. And of course, the series of those terms then is definitely just a constant multiple of the harmonic series. The harmonic series diverges, therefore that thing diverges. So the first part of the test, yeah, it came up that it was divergent, and then we found the original series was convergent, so therefore it's conditionally convergent. Okay, so that's the idea. Hopefully you will follow my my explanation. Follow my methods. The book's methods are fine, but I think my methods are a bit more concrete and programmable in a way. Anyways, here's they're talking about, yeah, the absolute convergence basically means you can reorder the terms of the series without really affecting it, but a conditional convergence, you can't pull that kind of stuff, sadly enough. Okay, so there's those last end notes, and then they go to homework. All right, I think I gave you the video quiz. I'm hoping I did. Where was it? Yeah, I did. Okay, so that'll do us for this video. Thank you for watching as usual, and I'll see you next time.